transfer standard so that it's capable of validating the CMCs of the laboratory participating in the PT. So it's very, very important that the selection be made correctly of the transfer standard. Otherwise, it's just futile to do an exercise of this sort, because if it doesn't have the right amount of metrological characteristics, it's just going to blur the picture and you won't be able to see almost anything. So the selection should depend on who the participants are. So if your participants are laboratories which are active in the area of, I don't know, maybe 0.1% of reading, and you use as a transfer standard a device which has a resolution of 2 units or even 1 unit, then this is not an ILC really, because you're not going to see anything. This finite resolution is really going to prevent you from seeing any of the other metrological characteristics being tested, and you won't be able to see the capabilities of the lab, which are at 0.1%. Yeah, you won't be able to see the capabilities of the lab come to the surface. So it's very, very important to select a transfer standard which will not desensitize, let's say, the whole procedure. And one way of making sure that you select the right transfer standard is to use a questionnaire which you circulate as a provider or an organizer, if you like, of an ILC or a PT provider. You circulate the questionnaire to see what the needs of the labs and the capabilities of the labs might be. Okay, and then you can plan what type of transfer standards you're going to be using and what type of ILCs you're going to be organizing. Are there any other questions with regard to this? So this is the first issue, the selection of the transfer standard. Very important. I have seldomly seen an ILC where a transfer standard was used which was adequate for the job. Typically what is done is the lab has a piece of equipment lying around. They say, okay, we'll use this. And they use it as a transfer standard, they measure it, they send it to the reference lab, and that's it. So that's really not a correct way of doing an ILC, and certainly not a PT. Okay. After the selection of the transfer standard, it's important to determine how stable this thing is. Because remember, we said that what we are trying to do in an ILC is we want to create the conditions so that everyone in the cycle measures the same thing, okay? So obviously, if the transfer standard is not stable, then they're not going to be measuring the same thing. Of course, in many instances, it can be corrected, but again, that's an approximation. That's additional uncertainty that someone will have to introduce. So based on its technical characteristics, the transfer standard should also be stable, okay? There's also the issue of homogeneity in general, which is important when we're talking about proficiency testing in testing lab um, applications. So there, it's important to ensure that the samples that are made available to the participants are homogeneous. So one participant doesn't get samples which are different from another participant. So on the average, they should be the same. So homogeneity is equally important for testing as stability is. For calibration, it's not that important because really we have a device in calibration which is circulated. But homogeneity takes a different um, uh, turn in calibration, and we'll see why. So with regard to these two issues, the homogeneity and the stability of the transfer standard or the artifact, um, criteria must be established based on the effect that inhomogeneity and instability will have on the evaluation of the participant's performance. So it has to be decided beforehand what the impact of any inhomogeneity or instability in the transfer standard might have on the results of the PT output. So all of the requirements in 17043 which deal with homogeneity and stability are intended to ensure that participants receive comparable PT items, okay, which remain stable throughout the PT. This is of the utmost importance. Otherwise, so two things. One, the item should be fit for purpose, and second, it should be stable. Um, so if for some reason that cannot be attained, then the uncertainty that they introduce into the process has to be included um, in the evaluation of the results and the participants' performance, because um, yeah, the instability is not due to the capabilities of the participant, but it's to the drawbacks of the device which is being used. So PT items should be stable to ensure that they will not change significantly throughout the PT ILC. When this is not possible, stability shall be quantified and included as an additional component in the measurement uncertainty of the assigned value of the PT item. So to begin with, we want to avoid instability, but if significant instability is present, we have to include an uncertainty component to um, allow for it. So this is kind of a similar distinction which is made between the uncertainty and calibration and that in use. Okay, so I don't know if you're aware of it, but in general, there are two types of uncertainties. There is the uncertainty which is included on a calibration certificate, and that is usually termed the uncertainty at calibration. And there's the uncertainty that we estimate um, um, corresponds to the measurement, to values, to measurement values, which are produced with it when we use it. Okay? So the uncertainty in use is, in general, larger than the uncertainty at calibration. Okay? In fact, yeah, because you have to take into account the specifics of your lab where the piece of equipment is being used. So this is kind of reminiscent of what I just finished talking about the stability and the inclusion of a component of uncertainty for the lack of stability in the uncertainty of the efficiency testing scheme. So what about homogeneity? As I said, it's very important when we're talking about materials which are being used as samples, and this is true for construction materials, for foodstuffs, for what, anywhere where you have samples and they're being tested. The homogeneity is important because every one of the participants should be measuring the same thing. Um, in calibration, it's not that evident what is meant by homogeneity. Okay, in fact, homogeneity is pretty much has the same meaning in this case as the definition of the measurand. So, calibration artifact is more homogeneous the better that the measurand is defined. So remember, the measurand is a physical quantity, but it's not just a physical quantity. It's the physical quantity plus a set of rules on how to measure it. So the more you restrict the the way that this physical quantity can be measured, the more homogeneous is expected that the results produced from this instrument will be. Okay, so homogeneity and a good definition of the measurand are, again, very, very similar meanings in calibration. So for example here, we say that the measurand of the PT is the electrical resistance of the artifact at a temperature of 25 degrees and the pressure of standard atmosphere. The test current is not to exceed 10 milliamps for the 100 ohm resistor and 150 milliamps for the 20 ohm resistor respectively. So all of this information constitutes a measurand. Okay, it's not just the electrical resistance. A measurand is a value plus additional information. So how do we deal with stability issues? Since it's not always possible to estimate the uncertainty due to a particular condition of stability, we measure and evaluate the artifact stability during the PT rounds. This is why in many instances, transfer standards are measured at least twice, once before they leave the pilot lab and once after they return. Depending on the type of circulation scheme, it could be more than twice, but at least twice. So how do I estimate uncertainty with regard to instability? So here are three different situations. In the first case, the top, I have values which are all dispersed around a horizontal line, which is the average, it's the mean. So that's a fairly stable, there's no, actually there's no systematic influence on this artifact. If I wanted to include a component for instability because of this random variation around the mean, then I would need to include the pooled standard deviation, which is the best estimate of the type A uncertainty in this situation. So what's the pooled standard deviation again? Well, it's the average of all of the standard deviations from all of these tests that were performed. The second case is that I have a change in the value. And it's a gradual change. It's not an abrupt change. So we have a trend. This is termed drift. So we might have an instability which has the form of a drift. Okay. This is a nice drift because it's linear. And in order to determine this drift, we can determine um, the slope of the best line that approximates my points, and um, the y-intercept of the line, and determine the uncertainty which is associated with this best straight line. So that uncertainty then can be used as the uncertainty of the drift. This is one possibility. There are other possibilities also, but I think this is the most fundamental. You use your data in order to um, obtain information with regard to your measuring system. So in this case, you use all of these repeated measurements that you've done over time, and you determine the drift quantitatively by fitting a straight line and finding the uncertainty of the straight line. What's the uncertainty of the straight line? It's how much of this variation is missed by the straight line, right? It's all of this random dispersion around the straight line that still exists from these points. The third type of instability is a jump. So I might have up to one time a certain value, and then something happens, I don't know what exactly, and then the values from then on are dispersed around a different average. So then how do I include the uncertainty for this type of a jump into my proficiency testing uncertainty? Well, by rectangular distribution, you should try to avoid anything else unless you have very good reason to use something else. You should use a rectangular distribution. So it's the half jump divided by the square root of 3. Okay. So stability is very, very important. During the design phase of the PT, the artifact stability should be considered and its magnitude estimated and compared, if possible, with other uncertainty components of the reference lab. It should be judged if the stability uncertainty is suitable for validating participant CMCs. So obviously, if the instability uncertainty is large enough, it will again blur the picture. It won't let you make clear, have a clear picture of what the situation is. Measurements after the PT completion should validate the initial estimates and the established limits. These things are seldomly done. They're done by accredited proficiency testing providers. They're really not done by many other providers who are not accredited. And it's one of the drawbacks of, you know, it's getting there, but it's still a new system. So you have to establish magnitude, and then you have to validate after the completion of the PT that these established magnitudes of stability, in fact, are upheld. Okay. What type of circulation schemes are used in order to maybe increase the instability information that someone might get from the circulation of the transfer standard? So the most conservative design, which allows stability to be determined with the greatest confidence and smallest uncertainty, is the pedal design. Okay, so the pedal design, probably something like this, where we have a reference lab and the participants, and we have the transfer standard going back and forth between each participant and the reference lab. So the advantage is that it gives the greatest confidence and the smallest uncertainty, but nothing is free. So the disadvantage is that it has high costs, and it might take forever until this PT scheme is completed. There are variants on this in order to make it a little more expedient. Um, so it could be that besides the reference lab, so it won't have to do all of the work of stability measurements. Besides the reference lab, there is also a pivot lab, as it's called, which basically is its standards are calibrated by the reference lab, and then the pivot lab is the one that does the checking of the stability of the artifact as it's circulated back and forth between labs and it. So another situation might be where, because of the number of participants, for example, we do a multiple pedal design. So there's a, this happens, for example, in RMO key comparisons, where RMOs are large with a lot of labs in Euromed, for example, or where the distribution of the geographical distribution of labs is huge, like APMP. So you have a reference lab, and then you have several pedals of labs which perform the measurements sequentially, and once they finish, they send the transfer standard back to the reference lab for it to be checked for stability. The same is done for a second pedal, and the same is done for another pedal. Okay, so this is more expedient, and it saves a lot of time, actually, with regard to the work placed upon the reference lab. So what's the disadvantage here? Disadvantage is that if a common assigned value is necessary, okay, then it's a heck of a job to try to determine what that might be by using the values from the different pedals here. So it needs a lot of work with regard to the evaluation of the results. Okay, what's the most applicable circulation scheme is the ring design. Artifacts are expected to exhibit good short-term stability. The advantage is that you keep costs and the duration to a minimum, but there is a risk of losing data if the artifact becomes unstable at some point during circulation. There are variants to all of these. For example, now what comes to mind is that in the 1 kg mass comparison, key comparison that we did in GulfMet, two standards were sent out. And it was required that the difference and the sum of these two standards was determined. Okay? Both of these are indicators. Well, the first one is an indicator. The difference is an indicator of the stability of the transfer standard. And the sum is an indicator of the stability of the participants' reference standards. So there are variants to all of these systems here, which are used in order to reduce the risk, really. Okay, with regard to the assigned values, so the definition of the assigned value is that it's a value attributed to a particular property of a proficiency test item. So we have to be careful here with this definition because it doesn't say that it's determined by the provider, or it has to do something with, it could be anything that the provider decides to assign to this particular property that's being measured. Usually, this is a reference value, okay? And the way that this reference value is determined, in calibration at least, and the way that this reference value is determined could be anything. So it all depends on what the accepted international practice is and good judgment based on expertise of the provider who is organizing this proficiency testing scheme. In addition to having an assigned value, there's a requirement that proficiency testing schemes in the area of calibration shall have assigned values with metrological traceability. Okay, so the assigned values should be traceable, and they should include a measurement uncertainty estimate. So the assigned value is actually what the participants are judged against, okay? It usually is a reference value. In calibration, this reference value has to have metrological traceability, and it has to be associated with a measurement uncertainty. So there are different procedures available in order to determine an assigned value, okay? And they're listed here in an order of increasing uncertainty. So the first two actually have to do with values based on coming from the area of testing, where we might have known values by formulation, so a chemical composition, okay? Or certified reference values. So the materials are produced as certified materials. This is not the case in calibration, really. So this is mostly relevant to testing in chemical, the analytical chemistry area, and the medical area. Okay, what are the possibilities of assigned value for calibration? Reference values, consensus values from expert participants, and consensus values from participants. So the one category that most of us are more accustomed to is the third one, where typically the consensus value in is built up from all of the participants. So in many ILCs, the assigned value, if we can call it an assigned value, is built up from the some kind of a pooling of the results of all of the participants. It depends on the method of value assignment I will use. It depends on the type of proficiency testing or ILC that I am running. let me say proficiency testing because the assigned value is pretty much related to proficiency testing, okay? Reference values are more related to calibration and comparisons. So, okay. Right. So I will not, for example, decide to use a consensus value from all of the participants in a proficiency testing scheme where I am trying to validate the competence of the participants. I will probably use a reference value coming from some external source, okay? Or if the scheme is designed in such a way, I will have expert participants who I will use their results to form a consensus value. So typically, in proficiency testing, the consensus value from participants is to be avoided. So that's another difference from ILCs. In ILCs, typically, the reference value is built up out of all of the values of the participants. Why? Because it's acknowledged that all of the participants know how to measure this particular quantity. However, in proficiency testing, it has to be proven that they know how to measure this quantity. Hence, their values cannot be used in order to form the reference. So you have to have a reference externally. If consensus values are used, outliers have to be controlled by statistically valid techniques. So anything that looks like an outlier, it has to be excluded from the calculation of the consensus value. So obvious blunders should be removed. If possible, minimize the influence by using statistical methods, use robust methods. All of these are tools that can be used to control outliers. It's not simple, particularly because in most cases, the weighted average is used as a way of forming an assigned value or a reference value. And the weighted average is notorious for being what's the word? For being prone to giving wrong results when outliers are present. So if we have a straight line which is fitted to data points using the weighted mean estimator, and you have an outlier, then this straight line is drawn to this outlier. So there is a certain amount of carefulness that has to be exercised. And this is where, again, the technical capability of the group of experts who are responsible for providing the expert information for the particular proficiency testing scheme comes into play. So in the case that a reference value, when would a reference value be used? So in order for a reference value to be used, it must be reliable. Okay, there must be a reference laboratory with the necessary competence. Again, what is this used for? As an assigned value for the proficiency testing scheme. It must have a low uncertainty so as not to affect the participant evaluation. Okay, so these are situations where the use of a reference value is favored. When would a consensus value be used? When a reference laboratory capable of providing a reliable reference value cannot be found. Okay, so you don't have such a lab. That's a rare situation, but it could happen in certain areas. When the uncertainty required is smaller than any of the participating laboratories. So if for some reason the uncertainty required in a PT scheme is smaller than any of the participating laboratories, then the only way around that is to use a consensus value, because when you take the average of all of these quantities, then the uncertainty will scale with the number of laboratories that are being averaged. When PT items' technical characteristics, e.g. resolution, can affect the performance evaluation. So in all of these cases, it's a good idea to, or it's probably better to use a consensus value than a reference value. Okay, so for a consensus value, I mentioned that least squares are used in many instances, weighted least squares, in order to form the consensus value. So I just want to go over a little bit the method of using least squares in order to form the consensus value and how it works. What are the advantages? It's relatively simple. It can model changes or instabilities of artifacts. Covariances can be taken into account. Different petals can be linked. All of these are issues which are readily dealt with the method of least squares. The disadvantage is that they are susceptible to the effect of outliers. So what are the statistical assumptions that are usually put into the model when someone uses least squares in order to formulate a consensus value? An assigned value through consensus. So there's no change of the artifact with time. Results are independent. A Gaussian distribution is assumed to the measurement of which each participant's measurement is an estimate. Okay, so not anything strange, typical assumptions with typical measurements. Okay, so let's assume that there are n laboratories with varying capabilities as reflected in their quoted uncertainties, and they make a measurement on a circulated artifact. So because you have a lot of similar things here, it's easier to deal with them in matrix form. So my measurement model will be that the error determined from each one of the n laboratories is equal to a vector of a unit vector where the ones in this vector are equal to the number of laboratories which are taking part in the comparison. And a sub 1 is the parameter which describes the measured quantity. So let me rephrase this again. This is the expectation of y is equal to x times a. So what is x and what is a? So a is the quantity that's being determined, and x represents all of the participating laboratories. So each one of these participating laboratories determines a value for A1. Okay? So what this says is that, very simply, that lab 1 has determined a value Y1 for A1. Lab 2 has determined a value Y2 for A1, and so on and so forth. So what are the data that the participants provide and are analyzed in this scene? It's their results and their uncertainties. So these are the numbers that they determine, and these are the variances associated with the numbers that they determine. This is called the covariance matrix. So if someone does a least squares adjustment to find what the best value of parameters is, so as to minimize the square of the differences between the measured value and the model value, which is, again, it's the least squares adjustment criterion, okay? The result will be that the reference value and its uncertainty are given by these expressions here. So this would be the weighted average, and this would be the variance of the weighted average. So what does this say? It says, well, add all of the participants' values, but don't put equal trust on all of them. Some of them should count more, and some of them less, depending on the uncertainty with which they have been determined. Okay, that's what the weighting does here. The next thing someone does in the method of least squares is to try to determine whether the measurements of each one of the participants is consistent with the calculated reference value. And in order to do that, the normalized deviations from the reference value are formed. And this is the measurement of lab I minus the reference value divided by the uncertainty of the difference between these two. And the uncertainty of the difference is this. Why? Because these are correlated and there's a minus sign here. Why are they correlated? Because this number was used in order to calculate the weighted mean. So there's a minus here, and we form what is called the normalized deviations from the reference value. So what does this help me do? It helps me to understand if a particular measurement is consistent with the reference value. If it's not consistent, then I have to take it out and recalculate the reference value until all of the numbers that participate in it are consistent. Okay, so I want to get rid of any inconsistencies that might influence the reference value. Why am I doing this? I'm doing it because, as I said, for weighted least squares, the they are very, very susceptible to outliers. So I want to, this is a method of taking away outliers so they won't distort the value of the reference. Okay, I won't go into more technical detail here, but just to give you an indication, so this is information obtained from this paper. So here we have the results of an ILC. I think it's in mass, I'm not sure. And the two red lines are the uncertainty of the reference value. The reference value is the central green line. And in the graph right next to it, you see the two red lines that delineate the region where these deviations have to be in order for them to be consistent with the statistical assumptions of the test that's being done. So in other words, the Y's have to be such, the measurements of the participants have to be such that their difference from the reference value has to be within those two red lines. So if it's not within those two red lines, then it should be excluded from the formation of the reference value. Okay, another estimator which is used in many instances is the median. And the median of the absolute deviation in order to express the uncertainty associated with the median. So what's the basic advantage of this estimator with respect to the weighted average? The basic advantage is that this is what is called a robust estimator. So it's not susceptible to outliers as much as the weighted least squares. It's relatively simple to implement. Okay, the main disadvantage is that you need a relatively large number of participants in order for this to have reliable, to be reliable in whatever results you get from it. So what is the median? To remind us again, the median of a continuous variate is defined as the value where 1/2 of the observations are below and the other 1/2 are above. Okay, so it's right 50% of the, right at the 50% point of the PDF. For a sample of n ordered variables, the sample median is denoted as x sub I and is defined as for odd number of variables as n minus 1 over 2. So what does that mean? It means that it's the value corresponding to the k equals n minus 1 over 2 position for odd number of variables. So it's the central number. So if I have 5 numbers, it's the third number. That's the median. On the other hand, if I have an even number of variables, then it's defined as 1/2 the kth plus k plus 1 variable, where k is equal to n over 2. So if the number of variables is 10, okay, then the median, then k would be 5, and the median would be the average between the 5 and 6 variables. So here then, you just pick a number from the existing participant results, and you call that the reference. You understand, the smaller the number of participants you have, the less reliable this thing is. So if you have 100 participants, it's much more reliable than if you have 10 participants. So all these robust estimators are very, very important, again, in proficiency testing schemes, which are related to um, uh, testing labs, where the provider analyzes the results of hundreds of labs at the same time. Okay, and these are very, very important estimators for them. For calibration, there are some instances. It was a big deal maybe 15 years ago. Nowadays, I don't hear it that much. Okay, so if you have the median as the estimator of the assigned of the reference value, then what's its uncertainty? Well, its uncertainty is given by this thing in the well, by 1.858 over the square root of n minus 1 times the MAD. So what's the MAD? It's the median of the differences of all of the measurements minus the median. So if you have 10 measurements or 11 measurements, the median is the 6th measurement. Then you subtract from each one of the measurements the 6th measurement, and you take the absolute value, and the median of that absolute difference is the MAD, the median of the absolute deviations. And that is used to estimate the uncertainty associated with a median. So, yeah. And there are, these numbers are not just pulled out of a hat. Well, today they are pulled out of a hat, but they are calculated numbers based on statistical assumptions. So this is another choice for an estimator of the reference value or the assigned value in terms of a proficiency testing scheme. Are there any questions? So many of you guys are involved in ILCs, correct? So how did you calculate the reference value? Hmm? I know how you guys calculate it. The others, I'm asking. You consider? Right. But that's when you do bilateral comparisons. Do you do any multilateral comparisons? Yeah. So I guess the rest of you don't are not involved in this, or you've never come across an ILC report, your labs or from other labs. So where do you get your ILC services from? From GulfMed. So who does the piloting? Who does the reference? Who calculates the reference value? Umen. Okay, so I think that they report how they do it, right? So how do they do it? The average, not the weighted average. In what area is this? In the dimensional area? Do we have anyone from different areas here? I think that typically it's done by the weighted average. This is what has um, is the general practice internationally. In particular, with regard to key comparisons, this is the mainstream way of doing things. Of course, there are situations where this is not adequate, and in this case, then someone has to look into more involved statistical techniques, uses of the median and Monte Carlo simulations in order to try to determine coverage probabilities and instead of uncertainty values, and base the results on that. But most of the work in key comparisons has to do with the weighted average, weighted mean, which is actually the expression that I showed you here. So this is the weighted mean, and it's uncertain, it's variance. Okay, so the next then part has to do with what are the statistics that are used in order to judge performance of the participating laboratories. So in calibration, typically the EN index is used, okay? In other areas in testing, other indices are also used. But in calibration, this is almost exclusively used. So basically, what does this say? It's a test of whether the reference lab and the participant are measuring the same item. Virtually the same item. It is really the same item, but um, has it changed in any way, or has it changed in a way they think it has changed because of the way that they're measuring? So this EN number really categorizes the measurement of a quantity. I think it's reasonable in that in the numerator, pairing them with the sum of the difference between these numbers to the sum of the uncertainties with which they have been determined is less than 1, so the difference is less than the sum of the uncertainties, then we can rest assured that the same quantity is being determined. If there's significant inhomogeneity or instability is detected by the reference lab, then the corresponding uncertainty components have to be considered in order to obtain a realistic evaluation of participant results. So in case of inhomogeneity or instability, then U reference becomes U sub PT, where PT now is made up of 3 different uncertainties. One is the reference lab uncertainty, uncertainty, and the homogeneity. Where, I'm sorry, I missed your point. Where? Here. Yeah. Yeah. In the what? I'm sorry? No, we include them where, you said? In the? You include the stability based on what? Based on technical specifications. So that, I mean, you don't have to. However, if you do it, then that's your uncertainty. But the provider, the lab that's responsible for analyzing the results, has to account for any instability noticed during the circulation. So yeah, I agree that if you also include it, then it will make things better for you because you'll have a bigger number in your denominator there. But then, okay. So this is a picture of what you're, yes, to show you how En might change because of a large instability or inhomogeneity in the transfer standard. So what I have plotted here is the En number on the vertical axis. And over here I have the relative uncertainty. So I have the fraction of UPT over U of the participant. And I'm considering up to 10 times larger. So UPT becomes up to 10 times larger. So here I have the situation, I have 3 curves. One is for an En number of 2 with no PT uncertainty. And you see that once I start including the PT uncertainty, it can come all the way down to 1. So something, I mean, it's a tricky situation, and this is why it's not good to have an unstable transfer standard, because it might be that someone has bad results, but passes a proficiency test because of the instability of the transfer standard. So this is what this red line is showing. The EN number was 2 to begin with for a stable um, artifact. And as the instability increases, the EN number drops to 1. Here, the EN number was a little bit over 1, so it on the limit doesn't pass. But once the instability kicks in, if it's someone is starting to take account of it, it falls all the way down to half, so it passes with flying colors. So yes, the instability uncertainty has to be taken into account. However, it can influence the results of the conformity assessment that's being done through this test. So someone has to be very, very careful. This is why it's always a good idea to have a fit-for-purpose, stable, and well-defined measurand as a transfer standard. Okay, just to give you an example here. Before we go into should we take a break for prayer or no? Huh? Yeah. Are we going to have a test today? No, I'm saying, are we going to have a test for qualification or no? Are we going to have a test for qualification? Because there's a test, right, associated with this. Okay. So who's going to grade these? Who's going to grade them? What's the passing grade? Yes, yeah, of course. How many questions are going to be there? How many questions? Will they be multiple choice? Yeah. Well, and what other way would it be? Without calculations, how can you do an uncertainty estimation?